maths, yeah. But nevertheless, we still cover it nevertheless, yeah. Um, and at some point, um, I guess towards the end of the lecture, we will revisit those maths, yeah, especially when we look into the stability of our control systems, yeah. Um, I'm not sure when you learn about Rope stability criteria or Bott diagram or Nyquist diagram, yeah. I cannot remember in maths which maths, probably maths 4, 3 or 4, I think, yeah. But we will revisit that, but not today, but towards the end of a lecture on control, probably in week 13. We will revisit that. Now let us see this schematic diagram for a stirred tank blending system. Yeah. In control systems, we use a lot of schematic diagram. Yeah. And then you can see a lot of lines, some of them dash line, some of them solid lines connecting um, one element to another, yeah, in this system, yeah? Or in this example that you see here, the stirred tank blending system. Yeah? In control systems, this is also known as the uh, PIND diagram, yeah, piping instrument, piping instrumentation diagram, PNID, piping and instrumentations diagram, PNID. So if you have already started or already completed your project on Pulau Triso, maybe you probably already included a schematic diagram like this in your assignment for Pulau Triso, yeah. and uh, and I'm sure that you have come across the terms PNID, piping and installations diagram, yeah, um, in your uh, effort to come up with a report for the Pulau Triso. So this is one example of schematic diagram we want to see. Yeah? So the dash normally to imply critical signal, and the solid line, yeah, with two slash on it is a pneumatic signal. Yeah? So the first arrow there on the left, yeah, that coming to the tank, yeah, so the inlet, and then the zero in the middle with a constant volume of V, yeah, or it could be a variable volume V, and then we add in the solution, another solution that is X2 and W2, which is controlled by a valve. So the symbol there before that arrow that going into the tank is a valve, yeah, and this actually controlled by pneumatic signal, yeah, and that actually reflects the set point as well, yeah. And then at the bottom for the output X and W, we have the flow coming out, yeah. And you notice that from AC to AC, yeah, there's a dash line, yeah, and AC to AC also dash line, yeah. And that is actually the electrical signal, yeah. So if you look at this simple schematic diagram, you are actually looking at it's actually reflect a feedback controller. Yeah. So what I mean from this diagram, you can see that X and W is actually give feedback to AC, which is where the set point being set. Yeah. And that actually will go to the valve which control the amount of X2 and W2 coming in into the tank. Yeah. This is a simple feedback controller if you want. So for this system here, yeah, if we do not have the feedback controller here, yeah, we probably will have one type of control called on-off controller, which is very simple and normally cheap. And in this case, we probably do not use it for this kind of stirred tank blending system, but probably it's more being used for example, for heating, for example, like you're having your shower, yeah, the water shower. If you're cold, you just increase the temperature, yeah, um, actually it's not temperature, it's actually the thermostat is the water heater. Yeah, so it's also similar to residential heating in this case, or domestic refrigerator. Yeah, and for on and off controller, they have limited use in process control because or due to continuous cycling of control variables. Yeah, so in this case, um, an on-off controller normally will lead to excessive wear on control valve because the process is continuous. So if you look at the schematic diagram now, for example, remember if there are the water that's coming into the tank, yeah, keep on flowing, there's no way to control this valve, the opening of this valve, yeah. So it continuously, then maybe the rubber or the O-rings inside this valve probably will run out over time, yeah. So that's what it means here, excessive wear on control. The examples of process where they require on-off control actually are things like the batch process control. Yeah. Where in this case we have the programmable logic controller. Yeah. And the other example is the solenoid in home heating unit. Yeah. So you increase the temperature by reducing the resistance in this in the solenoid for home heating unit or in a water shower, for example. And then the sprinkler systems also. Yeah. Or even in this case, to an extent, it's a cruise control. Yeah, you said, let's say you drive a car, but you said the speed of 80 is moving 80, yeah, which is possible now with the autonomous vehicles, for example, yeah? Self-driven car, yeah, or maybe in a ship, maybe, yeah, you set the speed at certain knots, for example, yeah, in an open sea, yeah, where the traffic at the sea probably not that heavy, yeah, because you're not near to the port, for example, in a big open sea, you can just simply uh, go in a straight line, maybe, and the movement in the sea is very much controlled so by the radar in the control room or the ship, for example. In this case, it is on and off, yeah, and maybe you can think of other examples also. Yeah? Um, do you have any idea? Different type of on-off controller. Uh, it is a automated control system, but nevertheless, it's between on and off. Um, just like a cruise control here. Any idea? Yeah. How about um, autopilot? Do you think it's also part of the cruise control? Autopilot. Once the pilot um, took off from the runway, yeah, and then they reach the cruising height and speed. Yeah, probably they just simply engage the control autopilot, and the pilot can probably take a rest. Yeah, until probably um, they almost arrive at their destinations. Then they will take over from the autopilot system. So in this case, they off the autopilot uh, systems and they are in command, for example. Yeah. There is one example. Yeah. So if you look into the in more detail on the on-off controllers, yeah. So normally the on-off controller having a synonyms with the two positions or bang controllers in here, yeah. So whether it's at the maximum or at the minimum, yeah. So when it's maximum, probably talking about when it's on, and the minimum is off, yeah. And error is defined as the set point minus the measured variable in this case. Yeah? So in this case, for a on-off controller, the controller output has two possible values, either max or the min, maximum or minimum value. in a practical case, when we have a dead band, this is what we call the dead band. When in this case, they said when the systems never reaches steady state, yeah, um, you try to, uh, for example, um, the ship or the car, for example, yeah, um, driving at a certain speed, yeah, on auto cruise, for example, but they never arrive at that speed, yeah. Some of them could be due to friction, maybe, yeah, and in this case, there are uh, some components where it will never reach that particular desired speed or the set point. Yeah? So that is considered as the dead band in this case, yeah? Tolerance from the error. Coming back to our flow control system. Yeah? For example, in the water coming into the tank, for example, the process stream going into the tank, yeah, which is controlled by the valve here, yeah, and the control valve actually monitored by um, flow transmitter, which measured the flow velocity, and also the flow controller. Yeah? And then we also have the schematic diagram of a feedback controller. Yeah? So we have input signal going into the controller in this case. So for this figure 8.3, when referring to figure 8.2, the controller here could be simply a flow controller here. So we set the set point YSP for the flow controller, whatever the flow that you require to be in the form of the flow rate or even the velocity in this case. Uh, Probably easier to set it for as a flow rate. Yeah. And then we have the input signal YM from the transmitter, this one here, which is actually measuring the flow across this process stream here. Yeah. And then the controller will try to uh, reach the set point, yeah, by functioning the error correct, and then that will give the output signal P that is to control the valve here in this case here. So this diagram, this line is referring to this one here, from FT to FC to the control valve, this one here. Yeah? So this is the schematic diagram of a feedback controller. Now we look into what it means with three mode PID controller. Yeah. PID stands for proportionals for P, then integral for I, and a derivative for D. Yeah. Proportionals in this case actually talking about like y equal to mx. Yeah. A straight line y to mx is a proportional. Yeah. You increase it based on the gradient of the graph. Yeah. So in this case, if you have YSP as the set point and YM is as the measured value of the control variable, then the error signal or the difference between the set point and measured value is actually reflecting the equivalent signal from the transmitter space. So since signals are time varying, yeah, so from our proportional equations, yeah, so if error equal to YSPT minus YMT, yeah, so it must be in second, if it is in a unit. Then for proportional control, we say that PT equal to P dash plus KC, the constant, and the control constants, and then times the error as a function of P. So we have P dash equal to P minus P bar. Yeah. So in this case, where PT is the controller output, P bar is the bias value or adjustable value. Yeah. And KC is the control gain, or which is it's a gain, so it's a dimensionless and can be adjusted. Yeah? And if you plot the graph, yeah, for proportional controller, it can simply a straight line, and it will give you the gradient will give you the value of the distance. Yeah? So the slope of the line is the uh, controller gain or KC case. Yeah? This is an example where you have the limit between Pmax and Pmin in this case. So we have proper definitions of proportional band to be that as a function of the controller gain Kc, so it's up of 100%, Kc is 100%. Then we also have a reverse or direct acting controller. Yeah. So the Kc can be made positive or negative. Yeah. So it's a direct uh, positive, reverse to be negative. Yeah. And if we recall for proportional feedback control, yeah, PT equal to P bar plus KT, PT, which is actually this is here, this one here, proportional control, yeah. So the P part, PID, P. Then we can rearrange it, become PT equal to P bar plus KC, the set point YSPT minus integration YMT. So this is for reverse or acting direct controller. For direct acting, where KC is less than 0, then the output increases as input increases. Yeah? And for reverse acting, where KC bigger than 0, the constant gain is uh, the proportional gain is bigger than 0, then the output increases as input decreases. So based on the first example, so now we move to the second example. Yeah? So this one here, we have this now we have this example. The first example, FT here, FT here, the graph here. Now we have the second example, FT and FT, but in this case, we assume FT is a direct active, a transmitted direct active. So if you select the sign of KC, so that KC and KV bigger than 0, yeah? So in this case, if A to open the close valve, what is the value you expect? So that's what it means. And if A to close or fair open valve will be what is the consequences or the action uh, of the controller, yeah, for this particular actions. So this is the example that we want to study. So in this case, for a transfer function for this type of proportional control, yeah, if you let p dash t to p minus p bar, then the controller input or output relation can be written as p dash t to kc dt. Yeah. So for the constant controller constant kc function of the error, and the take Laplace transform of each sign, we have p dash s to kc e s. Yeah. So now we have in S instead of T we to S, if we apply the Laplace transform. And in this case, we have P dash S over ES equal to KC. That is for the um, transfer function for proportional control. Now we move to the integral control action. So integral actually talking about the based on integrations. Yeah. So also known as a reset or the plotting control. So in this case, the equation for integral contraction to be pt to the p bar plus 1 over 2 I times integration from 0 to t et dash dt dash. Yeah? So in this case, p dash s over es equal to 1 over 2 1 s. Yeah? So I is the reset time or the integral time and can be adjustable. So this is for integral. Why? Because we want to look into if we have a system which combine both proportional and integral. So if we have proportional and integral control system, so we have Pt now becomes P bar plus Kc times Et plus 1 over 2 I and from 0 to t Et dash dt. Yeah? And in this case, the integral provides memory of the error and normally in control systems, this is one of the most popular controller, yeah? Proportional integral control together. So if you respond to unit state change in this example, then we have the KC, the constant gain here, and then the slope will give you the integral part x2 over to I. Yeah. So this is the response of proportional integral controller to unit step change in Vt. So in this case, you can say that integral actions eliminate steady state error. Yeah? But the question will be why? Yeah. So if you look at this graph, yeah, the set point as a function of time. Yeah. So when you apply proportional and integral control, yeah, where the control function now become p dash s over es equal kc times 1 plus 1 over 2 is. Yeah. You can see that over time, the control variables, yeah, will be near to the set point here. Yeah. So it will eliminate steady state error in this case over time. Yeah. So you can see that the proportional together with the integral part that will eliminate the steady state error. So some controls also are calibrated in 1 over tau I. Yeah. Or in other words, it's considered 1 over tau I is the repeats per minute. Yeah. Instead of tau I, the integral time Ti. Tau I. So for a proportional integral controllers, P bar is not adjustable. Yeah. So because of that, we need to consider another type. They call it derivative control action. Yeah. So for derivative control action, yeah. So derivation, derivative derivation is now dE over dt. Yeah. So in this case, our Pt is equal to P bar plus tau d times dE dt. And we use to improve dynamic response of the control variable. And we can also have what's called derivative,
Tiga kelas.
which is minus dym over dt. Yeah. But the only question that will come back to will be, can we use the derivative control
Oh, kau ni terkejut aku.
on its own or alone? Yeah. Can we do that? Yeah.
Dia dah bagi sebagai daripada.
So this is the unit, the derivative control dE dt used in here. Yeah. In this case, we can use the noisy signal. Yeah. So if there is a noisy signal, you can apply the derivative controller. Yeah, and you can filter it out. Yeah, for noisy signal. So in this case, we have 1 over tau 2s transfer function 1 over tau 2s 1. So if we combine all three, the proportionals, integral, and derivative control modes as a PID controller, yeah, and there are many variations of PID control used effectively, but we consider the three most common forms. The first one being the parallel form of PID control. Yeah? So the parallel form of the PID control algorithm we have a derivative filter explained by this equation. Yeah? Where they are considering for the proportional, yeah, integral, yeah, and derivative. So this is for the parallel form. Yeah, all three in action, the proportional, integral, and derivative. So in this case, our target is the transfer function is given by this equation p dash s over es equal to kc times 1 plus 1 over tau is times tau s. Yeah. So this is for parallel. Yeah. So controller in parallel, for example. Yeah. But if you go for controller in series, the series form of PID control, yeah, which historically it is convenient to construct early analog controllers, both electronic and pneumatic, so that a proportional integral element and a proportional derivative element operated in series. Yeah. So instead of parallel, now we have it in series. Yeah? So the commercial versions of the series form controller have a derivative filter that is applied to either the derivative terms, given the equation 8.12, yeah, which is actually 8.15. For the PD term, okay, for the PD term, um, I don't have this, it is 8.12, but we have 8.15, which is this one here, the PD term, proportional and derivative term, this one here, between equations 8.15. And then we also have the expanded form of the ID controller. Yeah? So what it means, the expanded actually, in addition to the series and the parallel form, the expanded form is used here, yeah, with these equations here. So we have, this is the expanded form of the ID controller. And when we look into the general or the features of the PID controllers, the PID controllers will eliminate the derivative and proportional kick. So in this case, it become a disadvantageous, yeah, of the previous PID controllers, that a sudden change in set point and therefore the error E will cause the derivative term momentarily to become very large and thus provide a derivative kick to the final control element. So this is the key characteristics of commercial PID controllers. Yeah? We have proportional mode, integral mode, and derivative mode. Where for proportional mode, we have for the controller parameter with the controller gain KC, proportional gain PB, which is out of 100%. Units for all controller gain in this case will be, for proportional mode, will be dimensionless. The range of 0.1 to 100, and the percentage or the proportional gain from uh, from 1 to 1000%. For integral mode, yeah, the integral time or the reset time given by tau I, yeah, so the unit for that parameter will be minute or in second. So it's from 0.02 to 20 minutes, or from 1 to 1000 seconds, yeah, the range. And the reset rate will be one. The reset rate is 1 over tau I, which is a repeat of time. So it's over 1 over the time, so it becomes uh, minute or 1 per minute of per second in this case. So it will be range from 0.01 to 1 repeat per second, or 0.06 to 60 repeats per minute. That's 1 minute, that's 60 seconds. And the integral mode gain, AI, in this case, will be 1 over time. So per minute or per second, the range from 0.1 to 100. Whereas for derivative mode, with the derivative time, so d, and this is the time, so it's either in minutes or in seconds. The range from 0.1 to 10 minutes or 5 to 500 seconds. Yeah? And for derivative mode gain, kd will be time minute per second from 0.1 to 100. Whereas for derivative filter parameter, which is dimensionless, so, um, or is dimensionless, the range will be from 0.05 to 0.2. Yeah? And finally, we have control intervals, and this will apply to the digital controllers. So the interval given by delta t, we unit time in second, ranging from 0.1 second to 10 minutes. So we now look into both automatic and manual control modes. Yeah? So initially we look into the manual one, on and off, and then we move to PID, which is automatic. Yeah? So in this case, for automatic mode, the controller output PT actually depends on the error EP and the control constant and the type of controller used. So for example, you want to compare between proportional integral against proportional integral derivative, or PI or PD. And for manual mode, the controller output PT is adjusted manually on and off to the minimum and maximum value. And for manual mode, it is very useful when unusual conditions exist. For example, for plant startup or for plant shutdown, as well as for emergency. Yeah? So the percentage of the controllers, in this case, which is manual or which is automatic, yeah? Based on Honeywell. Honeywell is a well-known um, control system manufacturer. Yeah? In 2001, they mentioned there are 30% uh, of controls actually still on manual. Yeah, there is 2001. Now it's 2020, 20 years after. So based on our pursuit for automation, I believe that 50% probably already reduced to less than 50% now. Yeah, there's a lot of things happening in the past 20 years. Yeah? If you look into a bit more detail on a digital PID controller, yeah? So this is the equation for digital PID controller, where we have the finite difference approximation